Good morning 12th class. This is third video regarding to imperfection in solids. Hope so that previous video both the topics clear to you. Okay, now today's our topic is point defects in non-stoichiometric crystals. Okay, now in case of non-stoichiometric crystal, I think you know stoichiometric compound in which the ratio of positive and negative ions are not disturbed. So obviously non-stoichiometric crystals means okay, it's opposite of stoichiometric crystal. So in this defect, generally these defects arises when stoichiometry of a substance is disturbed. It means the ratio is not same. Okay, now but it's not necessary. So in case of a non-stoichiometric crystal, the ratio of positive and negative ion is not same. Okay, that is non-stoichiometric defect. Okay, now these defect basically non-stoichiometric crystal, so that one is again classified into two type. Okay, one is it's a metal excess defect and another one is metal deficiency defect. Okay, so one is metal excess defect, one is metal deficiency defect. Now in case of metal excess defect, okay, that one is again due to, okay, one is due to anion vacancy, another one is due to interstitial cation. I'll explain both the topic in detail. Now first of all, metal excess defect. Now just see, in case of metal excess defect, okay, first of all, metal excess defect due to, this one is due to anion vacancy. Now just see, this one is a crystal, again it's arrangement, positive negative positive negative. Now just see, okay, so from this, that one is one anion is missing. Okay, because it's again that metal excess defect. So how is it possible that there is a metal excess defect? Okay, actually metals means those who have tendency to lose electron and acquire positive charge. So those who have more number of cations, okay, and as comparison to anion, so that will shows metal excess defect. So in this one, okay, how is it possible? Metal कैसे ज़्यादा हो सकते हैं? Basically positive ion. Okay, how? So either negative ion means anion leave their site, okay, or either second condition is कि extra cations are added in the interstitial site. So first one is when anion leave their lattice site. So now just see in this one, due to anion vacancy, now anion leave their site. This one is okay, when anion leave their site, the electron gets trapped in the anion vacancy. जैसे इसमें से इलेक्ट्रॉन गया, जैसे इसमें से एनायन गया, देन इलेक्ट्रॉन इज ट्रैप्ड इन दिस वन एनायन वैकेंसी एंड दिस इज नोन एज एफ सेंटर्स. Where electrons are trapped, that one is known as F center. So how to define F centers? Okay, these are the anionic sites occupied by unpaired electrons. Okay, that one is known as F centers, and F centers impart color to the crystal. Okay, F centers impart color to the crystal. You can take any example. Okay, generally that the crystal of NaCl, it's a sodium chloride, so it gives yellow color to NaCl, then pink color to LiCl, it's a lithium chloride, violet color to KCl. Okay, the F centers are basically, it's a electron trapped in anion vacancy, that one is F center, and that is responsible for imparting color to the different crystals. Okay, now this one is one metal excess defect due to anion vacancy. Now second is that metal excess defect due to interstitial cation. Interstitial cation means that extra cation goes to the unoccupied space. Now just see in this one, again it's a positive negative positive negative, but one cation, extra cation occupies interstitial site, and just because of that number of positive ion increases, it means in this that positive ion cation is more. Okay, that's why this one is a defect. Okay, this one is again that extra cation goes to the interstitial site, and at the same time that electron goes, one electron goes to the vicinity of interstitial site, or you can say generally इलेक्ट्रॉन टू द नेबरिंग इंटरस्टिशियल साइट. जो एक इलेक्ट्रॉन है वो कहाँ चला जाएगा? इसके नेबरिंग में. इफ़ टू कैटायंस आर ऑक्यूपाइंग इंटरस्टिशियल साइट, तो टू बैलेंस या सिंपल टू न्यूट्रलाइज इट, okay, two electron will occupy interstitial site. So this one is metal excess defect due to interstitial cation. Now this is generally when we heat, okay, you can take one example, that zinc oxide on heating loses oxygen and turns yellow. Okay, when we heat it, ZNO, that one is zinc oxide, heat it, then Zn2 positive plus oxygen is formed and 2 electron. These electrons generally, now just see the axis of Zn2 positive ion move to the interstitial sites and the electron to neighboring interstitial sites. So this one is metal excess defect due to interstitial cation. Now this one is one. Now another type of point defect in non-stoichiometric compound, okay, or crystal, that one is metal deficiency defect. Okay, again, metal deficiency defect means the number of cation is less. अब number of cations कम होंगे as comparison to anion. Okay, अच्छा ये कैसे possible हो सकता है कि how to increase the number of anion, negative ion ज़्यादा कैसे होंगे? Either the number of cation is less, means some of the cation leave their lattice site, or maybe some extra anions come to the interstitial site. Okay, although in this first possibility is more as comparison to second one. Acha, now just see, this one is, first is metal deficiency defect due to cation vacancy. In this also, okay, cation, anion, and one cation is missing from this site. Okay, and to maintain or simple, okay, to remain neutral, yeah, crystal remain neutral, generally charge, now just see this A positive become A2 positive. Okay, this metal acquiring higher charge. Why to acquire higher charge? To remain neutral. Okay, so in this way, that normally that cation is missing from this side and anion is comparatively more. That's why this one is metal deficiency defect. Okay, this type of defect is possible. Okay, generally this type of defect is possible, okay, which shows variable oxidation state. Yeah, metals which shows variable oxidation state. I think you know iron, for example, iron, it shows +2 and +3 oxidation state also. Okay, the metal which shows the variable oxidation state generally shows metal deficiency defect. Okay, in this example you can take either it's a ferrous oxide, ferrous sulfide, nickel oxide. Okay, in this case generally iron pyrites. Okay, iron pyrites, formula of iron pyrites is, it's a FeS. This one is iron pyrite. So in case of FeS, okay, generally 2 out of 3 ferrous ions, means Fe2 positive ions, okay, it's a ferrous ion, in a lattice may be converted into Fe3, means Fe2 positive ion may be converted into Fe3 positive ion. And how they converted? By losing electrons. Okay, now in this one, so they are converting into this, and just because of these conversion and all, generally that iron pyrite have luster, or either you can say they have shiny, okay, they have shine. Okay, and that just because of that shine, actually it shines like gold. Okay, सोने जैसा दिखाई देता है, it shines like gold, and just because of that, that one is also known as fool's gold. Okay, nickname होता है ना सबका. Okay, तो same condition, that is FeS is also, मतलब nickname of FeS is, that one is fool's gold. Okay, now this one is one type of this one is metal deficiency defect. Now another we have, that one is extra anions occupying interstitial site. In case of metal deficiency defect, one is either anion leave their surface, or either anion goes to, extra anion goes to the interstitial site. But keep it in mind, this is very rare, this possibility is very less, this type of defect is very uncommon. Okay, why? What's the reason? Because you know the size of anion is much more than the size of cation. Okay, that's why this defect is uncommon, or the pattern is same, that anion goes to the interstitial site and to maintain neutrality, that the one of the cation acquire higher charge or something. But this one is uncommon. Okay, why? Because anions are larger in size and generally they will not fit in the interstitial sites, क्योंकि gaps कैसे होते हैं, काफ़ी छोटे होते हैं comparatively. Okay, now thank you.